Transformers. Transformers consist of an iron core around which is wrapped a primary coil of wire and a secondary coil of wire. You'll see here I've shown the secondary coil with more turns than the primary coil, but it can be the other way round. More about this later. If we apply a potential difference across the primary coil, we'll get a current in that coil, which I've shown by these arrows. This will produce a magnetic field, and the magnetic field will be magnified by the iron core. The changing magnetic field passing through the output coil will induce an EMF in the output coil, which will then produce a current. There's only an output potential difference while the magnetic flux through the secondary coil is changing. If we use an alternating input potential difference, the flux will be constantly changing, and we'll get an alternating output potential difference. So we apply an AC as the input, and we get an AC as the output. Transformers will only work with AC. In this case, the secondary coil has more turns than the primary coil, as I mentioned earlier, and so the output potential difference will actually be greater than the input potential difference. We'll see why in a moment. This is called a step-up transformer. From Faraday's law, we know that the voltage induced in the secondary coil, which I'll denote like this, is given by the number of turns in the secondary coil multiplied by the rate of change of magnetic flux through the secondary coil. It can also be shown that the voltage in the primary coil is given by the number of turns in the primary coil multiplied by the rate of change of magnetic flux through the primary coil. As the same magnetic flux passes through both coils, we find that the voltage across the secondary over the number of turns across the secondary will be equal to the rate of change of magnetic flux, but this is the same as for the primary, so we can simplify to this expression. This is known as the transformer rule. When the number of turns on the secondary coil is greater than the number on the primary coil, the potential difference across the secondary will be greater than that across the primary, and this is called a step-up transformer. A step-down transformer has fewer turns on the secondary coil than the primary, and the potential difference will be reduced. Transformers are close to being 100% efficient. If a transformer was 100% efficient, the power out would be equal to the power in, and electrical power is given by current times potential difference. So we could say that the current in the primary coil multiplied by the potential difference across the primary coil will equal the current in the secondary multiplied by the potential difference across the secondary. This means that if the potential difference increases, as in a step-up transformer, the current must reduce in the same proportion. So if we double the potential difference, we must halve the current, and so on. Therefore, a step-up transformer reduces the current, and a step-down transformer increases the current. The efficiency of a transformer will be given by the power output divided by the power input multiplied by 100 to give a percent. Or we can write it's the current in the secondary times the potential difference across the secondary over the current in the primary times the potential difference across the primary times 100 to get a percent. Here's an example. A mobile phone charger converts the mains at 230 volts to 9 volts. If the primary coil has 2000 turns, calculate the number of turns on the secondary coil. Well, for this we can use this expression, and we need to rearrange because we want the number of turns in the secondary. Putting in the values given gives an answer of 78, or around 80 turns. If the phone takes a current of 25 milliamps, calculate the current entering the charger, assuming it is 100% efficient. Well, now we can use this expression, and it's the primary current we want to find. Putting in the values given gives a primary current of 9.8 times 10 to the minus 4 amps, which is around 1 milliamp. Transformers have a laminated core made out of many thin sheets of iron rather than one large block of iron. This reduces eddy currents, which would reduce the magnetic flux within the core and would also lead to energy losses through heating of the core. They also have low resistance wires to reduce the energy losses, and making transformers sometimes over 97% efficient.